Welcome, my Algebra 3 students. We're in Lesson 8. We're going to talk about statements of similarity. And Miss Tracy can't spell, as usual. Statements of similarity. Yeah, that looks atrocious. We're just going to erase that. I will just say it. Statements of similarity. There we go. All right, so a statement of similarity, we're talking about a couple of different things. In geometry, we have something called congruency. And congruency means, technically, it means equal. Not equal, equal. And that means you have the same sides and the same angles. And when you have those two things, then you have congruency. You have the same shape, right? So that is what congruency means. It means the exact same shape. Right? So this polygon is congruent to this polygon if all the sides and all the angles are the same measure. Then we have something called similarity, which we've talked about before in regards to similar triangles and similar shapes. Similarity is not the same as congruency. Similarity means that you have the same angles, but the sides are different. All right, we remember this from Algebra 2 and Algebra 1. So those are the two main things that you need to talk about or that you need to remember when we're talking about comparing shapes one to another, whether or not they're congruent versus whether or not they're similar. And when they're congruent, we'll use something like a tick mark, like for instance, in these two triangles, I'm going to draw two different triangles here. But let's just say that this angle is congruent to this angle. All right. Now these two might be different, but the tick marks show which angles are congruent, right? Now the triangles are not congruent, and right now the triangles are not similar because we only have one pair of angles that are the same. However, if I did this and this, which said that all three angles of this triangle are congruent to the three angles in this triangle, then we would have similarity, right? That's the difference. All the angles are the same, but the sides are different. If I did this, this, and this, this, and this, then that would mean I have congruency, because my congruency, I would be saying that I have this side and this side the same, this side and this side the same, this side and this side the same, and then the same three angles internally. So as a result of that, I would have congruency. Okay, that's the difference between similarity and congruency. So let's try this first example problem here. Let me clear the page, and I am going to pause to draw this for us. So in the triangle in example 8.1, we see that we have angle or triangle ABC. And here we have, I'm going to use a different color, we have a bisector that is being drawn, and for it to be a bisector, it means it has to cut the angle it is bisecting exactly in half. So if this is a right angle, then this has to cut this into two 45-degree angles. So we know the measure of those. I'm sorry, it's not a bisector. Let me undo that. If it were a bisector, that would be what it is doing, but that is not what it is doing at all. Instead, this is going to be the altitude. I read ahead too far. Sorry about that. So this is going to come straight from here to the bottom. It's going to be the altitude of ABC, triangle ABC. So it also becomes a right angle here as well, because it is perpendicular to the base AC. Because that's how we get the height, is we draw a perpendicular line from the base to the very top vertex of the uppermost angle in a triangle. So this is our point D on segment AC. So we are asked to show the following. And that just literally means we need to show the illustration of AD over AB is equal to C, and that proportional statement. And we have to figure out how to do that. So the first thing I'm going to do is I'm going to look at these three triangles. We've seen this shape before. It's not a new shape for us. I'm going to look at these as three separate triangles so I can start drawing some conclusions. And first I'm going to draw the baby triangle, which is ADB. So I'm going to A. D is the right angle and B is up here. And now I'm going to draw the middle-sized right triangle, and that is going to be a little bit bigger right here. Right. Let me adjust that base a little bit because it needs to be a little angle here, and that's D, but the leg that sticks out, the short leg, goes to B, and then the hypotenuse goes to C right here. And if you look, this is this triangle, but it's kind of turned over on its side. It's like it flipped and laid down. That's the same triangle. So now we're going to draw the big triangle, the daddy triangle. This big one all the way. Now here's my right triangle, and then this one, the right triangle is B. And the short side goes to A, and then the long leg goes up to the C. And you can see that here, okay? It's just a mirror image. It's just flipped around. All right, so there's my three triangles that I have here, and I have my reference here. Now, I know that in ABC, angle A is the same angle as in ABD, because they're the same angle, right? So I can draw that congruency there. Now in angle C is the same in both the big triangle here and BDC, which the same degree here and here as I do here and here, and I have the same degree here and here as I do here and here, which tells me that angle B here and angle B here, but they're congruent to the opposite. They're the opposite one. So this is going to be congruent to angle C here. This is congruent to angle C. And this angle B is going to be congruent to angle A. So in the picture, it will look like this. This one is congruent to A, and this one is congruent to C, and then both of these are right angles. So if you can visualize that, if you can see that here, be here, right? And then we know where all the right angles are. So there's my three triangles. There's my congruency statements all made. So now I need to be able to show what they're asking me to show. So I can relate the shapes to each other now through a proportional statement. So let me do the bases first. So is AD is equal to BD, which is equal to AB. Right, and so that is going to be AD is proportional to AB. Those three are the ones that are similar. So now I'm looking at the hypotenuse. AB is going to be proportional to BC, which is going to be proportional to AC. All right, so I can write that. So this is the hypotenuse here. So, and for the AD base, AB is the hypotenuse. For the BD base, B and AB, and by using the transitive property, if this one is proportional to this one, and this one is proportional to this one, then both of these are proportional to each other. So I can say that AD over AB is proportional to a logic from lesson 7 to pull this type of proportion statement from a figure like that. All right, let us look at example 8.2. We're going to be talking about some transversals that do something similar. Here's 8.2. So, and they do not have the same distance between them, but we know they're parallel lines because they are indicated. Remember, we talked about assumptions that you can and cannot make. If they weren't marked, we couldn't assume they were parallel, but because they're marked, we can. So I have a line here that looks perpendicular, so I can't assume that. All right, and this length is x plus 1, and this length is 13. And then I have another transversal here, and this one is labeled x plus 4, and this one is labeled 19. Now, we know due to the nature of the interior space between these two that there's a consistency there that's proportional. So we can write a proportion the way it looks right here. We don't have to do anything crazy. We can just say x plus 1 over 13 is equal to x plus 4 over 19. And if you think about it, the one in this interior space is going to be proportional to the one in this interior space. This transversal is proportional to this transversal only because they're within the same space. Only because they're in the same space. This angle of this transversal is what makes these two relative to these two, because they're within the same parallel lines. So now all we have to do is cross multiply and solve for x. So we're just going to do a little bit of algebra. So 19 times x plus 1 is equal to 13 times 19x plus 19 is equal to 13x 52. Okay, so now I'm just going to subtract 13x from both sides. And then I'm going to subtract 19 from both sides. Cancel, cancel. 33. And if I divide 33 by 6, I find that x is equal to 11 over 2 when I reduce by 3. And that is a solution. It's not a satisfying solution, but it is correct. All right, so let's talk about angle bisectors and side ratios. And this is bisectors, by definition, divide what they're cutting into two equal parts. That is the definition of a bisector. If it's just a line that's cutting it into two parts, it's not a bisector. It has to cut it into two equal parts in order for it to bisect. So we're given a shape here, and we're taught something interesting about this angle bisector. So here we have a line here, and it is going to bisect the angle, the vertex it is being drawn from. That looks pretty even here. So this is a bisector, and these two are congruent angles. So now I have side A, side B, side C, and side D, and side E. E is equal to E. So we really don't have to do anything with that. But there is a way that we can relate these other sides. There's two ways, actually. And the first way is from left to right, top to bottom. So left, right top to bottom. That's going to be A over B, C over D. That's the first way. And then we have top to bottom, left to right. So top to bottom would be A over C is equal to B over D. Now personally, I prefer this method just because it's very visual. It's A over the C, B over the D. But this would have to have a preference. For me, though, to set it up, it's just like when we did the transversals in the last example problem. It was really easy to write the proportion statement because it was visually indicative of what you were seeing. I mean, you could just visually put it into the right spot, just like this right here. So it's up to you whichever way you want to do it, but it's either left to right, top to bottom, or top to bottom, left to right, however you want to do it. All right, so let's do a practice this, and this is going to be example 8.3. Let me clear this for us. Actually, I think what I'm going to do is just, instead of drawing all these shapes again, I'm just going to put in the proper dimensions because the shape is actually very close. So we have A, B, and C, and D. And this is 10, 15, X, and 12. Now remember, we could either do left to right, top to bottom, or we could do top to bottom, left to right. And I'm going to use this one just because you'll see what I'm talking about when I say it's very visual. So you see how you have 10 over X? 10 over X is equal to 15 over 12. 15 over 12. There's my statement. There's my proportion. And it was really easy to set up because I just had to look at the figure. Let me put 8.3 up here so you know which one that is. Now we just solve. So 120 is equal to 15x. So we're going to divide both sides by 15. And we know that we can get 30 4 times, and 15 is 2 30s, so 2 times 4 is 8. So 8 is equal to x. All right, that is the value of x. That's all we had to do was find x. Method, to me, that's the easiest way to do it because it's very obvious. But let me show you, if you did left to right, top to bottom, it'd be the same answer. So left to right on the top would be 10 over 15 equals left to right on the bottom would be x over 12. So if you look at it, you're still multiplying the same numbers. You just have swapped these two. It's really the same problem. So 120 is equal to 15x. I mean, so it doesn't matter. You're going to get the same answer. The same answer either way is 8. And I think my pen tip needs to be changed. It's giving me a little hard time right there. So you can see either one works. So I just prefer the one that gets set up naturally. Let's do another one. So here, this one makes me laugh a little bit. This is 8.4. The book is trying to stump us, right? So we have another triangle here. Let me let it set up. There we go. And we have the angle bisector, but it's down here. It's in the bottom. Let me make that look about even. So these two angles right here are the ones that are congruent. And this is A, this is B, this is C, and this is D. We have 6, we have 14, we have 20, and we have X, right? So if it confuses you that whenever the angle bisector is not at the top, just rotate your paper. So here's what I'm going to do. I'm going to pretend I can't really rotate the screen of my computer, but what I can do is I can copy, and then I can paste, and then I can rotate it around, just like that, right? And I'm going to make it pretty close to the size I need. So now I can see my angle bisectors in relationship to A, B, C, D, right? And I can see my sides. So now I'm just going to write it the way I see it. And the way I see it is 20 over 14 is equal to x over 6. That's going to be top to bottom, left to right. So the top numbers and the bottom number on the left, and then the top number and the bottom number on the right. All right, so easy peasy. That's going to be 120 is equal to 14x. And when I divide both sides by 14, this cancels. I can't really divide that, but I can reduce it, and I get 60 over 7. 7 is a prime, so it doesn't go into 60. So the answer is 60 over 7 is the value of x, and that is correct. And that is all we have for lesson 8. I'll see you in lesson 9. And actually in lesson 9, we are going to start talking about proofs, and we're going to begin outlining some proofs. We're going to talk some more about congruent figures as well. But all of this that we've done, lesson 7, lesson 8, is readying your mind to get ready to outline some proofs. So I will see you in lesson 9.